This is our first video for Module 8 on reactions of alkenes, beginning with some of the fundamentals. So alkenes, if you recall, result from having overlap of p orbitals leading to a pi bond, and that pi bond is reactive in a nucleophilic way, electron donating way, Lewis base way of forming bonds, staying with the rules of electron arrow pushing, where bonds, electrons flow from higher electron density to low, forming and breaking bonds. If I turn this on its side and add some side groups here, we see that this reaction can take place where these electrons can form a bond forming. And recall that a molecule like HBr is polarized and therefore has inductive effects. So the delta plus hydrogen, in fact, can draw those electrons toward it. We can also say that those electrons attack and pull off this proton, thus forming this new bond here and leaving a carbocation in its wake at the other carbon, right? Because that carbon no longer is double bonded. And the reaction can complete with the bromine negative coming in and forming a bond there. And that creates this bond. And so if you notice, we have the net addition of HBr to the alkene. And so here's another way of looking at that net reaction, starting with the double bonded alkene. Addition of HBr simply goes to that. So you can memorize the net reaction and try to recognize it wherever you see it, but it's better to understand the mechanism to predict a host of similar reactions and just to understand what's going on better in order to learn new concepts as well. Now, the order of stability of carbocations is an important aspect of this whole process. As you see here, we have a tertiary carbocation, a secondary carbocation, and a primary carbocation. And the tertiary carbocations are the most stable. The secondary carbocations are sort of in between. They can form, but they're not preferred as much as the tertiary. And the primary carbocations are basically impossibly unstable. So in any of these exercises, if you encounter a primary carbocation, I would not carry that forward to the final product, because I don't think the primary carbocation can form without a whole lot of help, which we won't get into. The rationale behind the tertiary carbocation being the most stable is shown here. So a carbocation consists of an empty p orbital, unhybridized. So a carbocation is sp2 hybridized. And therefore, what do we know about sp2 hybridized carbons? They're trigonal planar. And so therefore, a nucleophile coming in to bond to a carbocation can attack from either face of the molecule. So some nucleophile generically shown here, Nu-, can form a bond to the top or the bottom face via that empty p orbital toward the plus charge, donating electrons. So why is the tertiary carbocation more stable? It's because of the electron donating ability of carbon groups. So a tertiary carbocation, like the one you see here, has 3 carbon groups able to donate electron density toward the plus charged carbocation. So those have a stabilizing effect. A primary carbocation can't be stabilized enough by just one carbon group. So an example of how this applies. We have a compound here. Notice the 2 carbons of the alkene have different groups attached. When the 2 carbons of an alkene have different groups attached, there's going to be one carbocation preferred over the other. The only time that it's equal likelihood is when both carbons are chemically identical. The first step of this reaction is the same as what we saw above. Electrons forming a bond, breaking a bond there. That forms a new hydrogen bond right there, leaving a carbocation right there, and that's a secondary carbocation. In working these problems, I would draw both possibilities. So the other possibility, and you can think of this alkene double bond here on the left as a door swinging one direction or the other. In the top example, the door swung upward. In the bottom example, it swings downward, I guess you could say, picking up the same proton from HBr. And these should be Br, I just noticed. Br, apologies there. And so that one is a tertiary carbocation, notice. So you draw both possible carbocations, and then you say, based on what we learned above, that the tertiary carbocation is favored. The bromine then comes in and forms a bond, completing the reaction just like we saw above, making this bond to bromine. And so that's the favored product. The less favored product, maybe you get some of this forming, because secondary carbocations are still possible, but probably not anywhere near as much the less favored product. Now there's a couple things to point out here. One is that the favored product is not chiral. Notice I'm looking for stereochemistry resulting from this. We always keep using what we learned in the past, so having completed that unit. Notice here we have suddenly 2 chiral centers being formed. So even though this is the less favored product, we can just analyze this for a moment. This is going to result in, if you recall from the end of the last unit, 4 different stereoisomers possible. So we're always on the lookout for this. They're all going to be diastereomers and enantiomers. And or enantiomers. And of course, with 4 different ones, you're going to get RR, SS, enantiomers of each other, RS and SR, enantiomers of each other, and then these are diastereomers of each other, if you point at those. So if you create new chiral centers, you have to be aware of it. Technically, if you're asked to draw all the possible products of a reaction, you've got to keep that kind of thing in mind if you've created chiral centers. And again, this compound down here is not chiral. We can do further pretty interesting analysis using this energy diagram. Same reaction as we saw just above. Starting material here, carbocation intermediate here, favored product here. So we're just focusing on that lower probability, I should say. Energy diagrams are looked at this way. So the energy climbs during the reaction usually to initiate it, leading to a transition state. I'm going to label this 1, transition state 1. This is going to help us understand reaction dynamics a lot better. From the intermediate, not transition state, intermediate, carbocation intermediate, you have a small energy hill to climb to transition state 2. Once it achieves transition state 2, it's all downhill to the final product. So it's important to distinguish between intermediates and transition states. Transition states are hypothetical, existing in fractions of a second of time, or less than that. An intermediate is something that can be trapped and actually isolated, bottled, and can even stay around in the bottle for I don't know how long. So it's a real thing. Transition state theory helps us explain and understand reactions, however. Looking down below here, transition state 1, and again this is hypothetical, would look something like this, where the double bond is in the process of forming a new bond to hydrogen, which is in the process of breaking a bond to chlorine. Forming, breaking, and again, it's actually sort of breaking over here too. This dotted line indicates bonds forming and breaking. So it's really not that hydrogen has 2 full bonds to it. It's like it's got a half bond on either side. So it's meant to indicate the dynamic process of these bonds forming and breaking if you could take a snapshot at that nanosecond or less. Once it gets past that transition state, this bond has fully broken here, and this bond has fully formed, and it's left a carbocation here. And that brings us to the intermediate shown there. From the intermediate to the final product, the hypothetical transition state is merely the forming of that bond from chlorine to the carbocation. That's a lot easier to see, maybe. So these transition states are slightly higher in energy. Then from here it's all downhill, and the chlorine to carbon bond forms. So there's a whole section of organic chemistry about transition state theory. But it's important to remind ourselves how much energy really does play a role in reactions. We kind of know that intuitively, but we want to start to be able to analyze that in general ways like this. So one more example here. We have an alkene to start with, reacting with HBr again, have the arrows shown. Draw both possible intermediates. So here we have a primary carbocation as one possible intermediate. And you should recall from above that that's not really possible. So then you draw your other possible intermediate, a secondary carbocation. That is possible. Then the bromine comes and forms a bond there. That's that bond that just formed. Remember, bromine minus, 4 lone pairs around it, right? If you need to draw those in every time at first till you get used to it, go ahead and do that. And this is our preferred major product. So we have a new word to introduce here at the end, regiochemistry. Regiochemistry is where do groups add, preferably. Actually, broadly speaking, regiochemistry is from like the word region. It's like where do things go? Where do things leave from? Where do things go to in reaction chemistry? So we know what stereochemistry is. Now we have the term regiochemistry. Synthetic organic chemists strive for regiochemical control. And I'm going to go ahead and add stereochemical control. For a synthetic chemist, the holy grail is to have a reaction that gives you 100% regiochemical and stereochemical control. In the next video, we're going to look at how regiochemistry is a problem to be solved by more complex synthetic methods.